Example, okay, a global positioning satellite or systems receiver can calculate its position on Earth within a few meters. It picks up radio wave signals from several of the 32 GPS satellites orbiting the Earth. Now it's radio waves. Okay, GPS satellites orbit the Earth in medium Earth orbit with a period of 12 hours. So we've kind of looked at a few of these now in the last few clips. Okay, so you've low Earth orbit, which would be an example, would be the International Space Station. You've medium Earth orbit, which is an example here of these GPS satellites. And then you have geostationary orbit, which is when the period is 24 hours and the satellite stays in the same position. So these are in medium Earth orbit, so they don't stay in the same position, and that's why you need a whole series of them. And when your phone or your watch picks up GPS, it's picking up a series of satellites, and it's using its position to those satellites to give your position. So it's quite an interesting setup, but not relevant to us at the moment. Okay, so now the period is 12 hours. Okay, so the period is 12 hours, so we'll need to change that to seconds, so 12 by 60 by 60. Okay, so that's 43,200 seconds. Okay, now you're asked for the height of the GPS above the Earth's surface. So once again, we're interested in drawing this diagram, and you'll be drawing this diagram a lot in these kind of situations, and you're told that height, you're asked for that height. Okay, you're asked for the speed of the GPS satellite. Okay, you're asked for the minimum time it takes the GPS satellite to travel from the satellite receiver on the surface of the Earth. Okay, now the GPS signal is a radio wave, so that'll be interesting later on. So we will be using speed of light there. Okay, so I'll watch for that. Okay, now it looks like we've nothing, but we have been given the mass of the Earth, so 5.97 by 10 to the 24, and we've been given the radius of the Earth, 6,371 kilometers, so 6,731 by 10 to the power of 3 meters, and I'm going to put that into the diagram as well. And remember, in these questions you're always aware that you have Newton's you've the universal gravitational constant sitting there in your tables, right? So there you go. So you've made your list, okay, and you're now asked for the height of the GPS satellite above the Earth's surface. Okay, so you have to go looking and decide, okay, what formula am I going to use there? Okay, so now in this case, the earlier part of the question had asked you for the periodic time, or to derive the periodic time. So in fairness, you had a hint in that you had this formula. Okay, but look at this formula. So you have periodic time, you're interested, okay? You're looking for the height, and you have the radius of the Earth. So if you've got the radius of the orbit, you'd be in business. You've been given the mass of the central planet, so you're in business. So this is your formula. As I said earlier in this, you were asked to derive that. Even if you weren't, you should have, when you're looking at your formula, that's the one you're interested in. Okay, so t squared is 4 pi squared r cubed over gm. So it's 43,200 squared equals 4 pi squared r cubed, which is what we're looking for. That'll get us most of the way to our answer. That'll give us this, and we'll get that then at the end. Okay, over gm, 6.67 by 10 to the minus 11 by 5.97 by 10 to the 24. Okay, so look, we'll just go through this one in full, just for a change. 43,200 squared. Okay, so you're getting 1.866 by 10 to the power of 9. 4 pi, now we 4 pi squared divided by this, so I'll tidy all that up. So on the right hand side we have 4 multiplied by pi squared. Okay, and we're dividing it by 6.67 exponential minus 11, and we're dividing it by 5.97 exponential 24. It would probably be neater to have used your A over B button, but anyhow, That's me being old-fashioned. So you get 9.914 by 10 to the minus 14. So r cubed is 1.866 by 10 to the 9. So that's multiplied by r cubed. Divided by 9.914 by 10 to the minus 14. Dividing both sides by that. Okay, so we're getting 1.866 exponential 9 divided by 9.914 exponential minus 14. Okay, so we're getting 1.88. 2 by 10 to the 22. Remember, to get from r cubed to r is the cube root of r, and that is available to us. Second function, this guy. Okay, and we're getting an answer of 2.66 by 10 to the power of 7 meters. Now that's the radius of the orbit. So the height is going to be the radius of the orbit minus the radius of the Earth. So the height is going to be that 2.66 by 10 to the power of 7 minus the radius of the Earth, which is 6.371 by 10 to the power of 3. Sorry, 6,371 by 10 to the power of 3. And we're getting a value of 2.023 by 10 to the power of 7. Meters. Okay, that's it. All right, so just to recap, hugely important to draw that. Okay, you were given the periodic time, so straight away you're looking at it. This formula, or t is 2 pi r over v, which isn't useful to us because we don't have v, and you're in business after that. Okay, the next part is the speed of the GPS satellite, so we'll just do it down here. Speed of the GPS satellite. Now, okay, so we can put in, well, we don't really have to put in anything. Okay, this is where, here we go, the formula I've told you to learn, that one. Okay, we have our universal gravitational constant, we have the mass of the central body, and we have the radius of orbit, okay, which is this guy. Okay, be careful here, it's the radius of orbit we're interested in here now. 2.66 by 10 to the power of 7. Okay, so we'll do that. 6.67 exponential minus 11 multiplied by 5.97 exponential 24 equals divided by 2.66 exponential 7. Okay, so you're getting v squared equals 1.50 or 1.49736 by 10 to the power of 7. And then you're getting v is just the square root of that, and you're getting a value of 3,869 or thereabouts meters per second. Okay, that's part 2. Okay, so let's look at part 3. Okay, I'm going to just do it over here. Sorry now, but we're saving the planet. Okay, the minimum time it takes a GPS signal to travel from the satellite to a receiver on the surface of the Earth. Okay, so let's get clear about it. You have the speed, okay, which is 3 by 10 to the power of 8, the speed of the radio wave. Okay, you have the distance travelled. Okay, so what's the distance travelled from the satellite to the Earth? It's h, okay, which was 2.023 by 10 to the power of 7. Okay, so your v is s over t. So 3 by 10 to the power of 8 is equal to 2.023 by 10 to the power of 7 over t. So swap those, 2.023 by 10 to the power of 7 over 3 by 10 to the power of 8, and you're getting a value for t of 0.067 seconds. The magic formula that we constantly use. It comes up all over the place and it's not in the maths tables. Okay, so in that case, like there's a thought involved there, okay? Now, and I'm going through this very quickly, okay? You have more time to do this in a real world situation. Okay, so let's look at the last two. I won't write them down. Explain why GPS satellites are not classed as geostationary satellites. Well, their period of rotation is 12 hours, not 24 hours. And you would also say, so you'd say that, and you'd also say geostationary satellite. Now you get full marks for that, but you always repeat then geostationary satellite is 24 hours, the same period as the sun, has a period of 24 hours, the same period as the sun, as the Earth. So therefore, the satellite appears to stay in the same position over the Earth's surface at all times. Crucial one to know, and you'll need it for your assignment as well. Okay. And finally, this is not linked to mechanics, but let's look at it. Radio waves such as used by GPS satellites at the lowest frequency. What type of electromagnetic radiation is next lowest? Well, you go up and it's microwaves is next. And they also accept infrared, because microwaves are sometimes classed as infrared, but microwaves is where we'd be going with that, next lowest energy. Okay, right, that's it.